Welcome back. This is part 3 for the 1.2 PAP Precal notes. So we're going to pick up now on what's called piecewise functions. So a piecewise function is pretty much what it sounds like. It is a function that is in pieces. So it's made up of separate pieces. So I could have like a linear function and a quadratic function, and we put them together to form one function, and that is called a piecewise function. So when you see the equations that represent each piece of your whole graph, they're going to look like this. So this would be two different pieces. There's one graph of a linear and another of a quadratic, and we're going to join them together. Then you're also going to see these commas with some kind of restriction. So like x is less than or equal to 1, x is greater than 1. So that's going to tell us you can only go this certain amount on the graph for this particular piece. Just a quick inequality review. When you see less than or greater than with no line underneath and you graph it, you use an open circle. And if you see the equal to sign and you graph it, you're going to use a shaded in circle or closed circle, which just really looks like a point, a normal point on your graph. So if I want to really analyze what these restrictions mean, when it says x is less than or equal to 1, then what that's saying is that so when I graph negative x plus 1, I only want x's less than or equal to 1. Less than or equal to 1 on that graph. So we would go to 1 and we would only use everything that's less than 1 in that section for this particular graph. So then the same thing here, when it's x is greater than 1, when I graph x squared, I only want the x's that are greater than 1 on the graph. So we're going to go ahead and plot it, but I'm going to use the table to help me get the points. So if you know what your parent functions are and you know your critical attributes, then it makes graphing the piecewise a lot easier. If not, you can use a table and plug in some x values to get your points. So we're just going to plug in these x values to our first equation, negative x plus 1, and get the y values after we plug it in. So if 1 plugs into x, that would be negative 1 plus 1, which is 0. Negative 0 plus 1 is 1. And then negative times a negative 1, so that actually becomes positive 1. Plus 1 gives me 2. A negative 2 is really a positive 2, plus 1 is 3. And then a negative 3 is a positive 3, plus 1 is 4. So the second piece, the quadratic, 1 squared is 1, 2 squared is 4, 3 squared is 9. And I'm going to take these points now and plot them. So at 1, 0, I'm going to put a point. At 0, 1, here's a point. At negative 1, 2, negative 2, 3, negative 3, 4. So that's all we have for that table. And then I'm going to look at my restriction too. It says I only want the x's that are less than or equal to 1. So that gives me a closed circle at 1, and then all of these going this way. So that means the graph, even though it might extend down here, that gives me x's that are this direction, and I don't want those. I only want the ones that are less than. So I'm going to continue on the graph throughout the page, and I'm going to graph it now because I know these are the only ones that are going to be that x. It satisfies the restriction. Okay, graphing the quadratic one. We've got 1, 1. So I'm going to hold off there before I put a point because I already have a closed point from the first graph, and you'll see a pattern that happens with your piecewise. If you're not connecting directly at 1, 0 to do your quadratic and it skips up here somewhere, one of them is most likely going to be open and one is going to be closed. So I'm just going to put a little dot there just to save it as a spot, and then I'm going to use my restriction to figure out if that's an open or a closed circle. So then I have 2, 4. And then I have 3, 9, which is going to be up here off the graph somewhere. My restriction says everything greater than 1. So that means all the x's that are in this direction, I want to graph, which means I don't have to fill out the rest of the quadratic on this side because that would be everything less than 1. And notice there's no equal to sign. So this is in fact going to be an open circle there, not a closed circle. So then when I graph the quadratic, it's going to go upwards like that. And there is my piecewise graph. So it's two pieces to form one graph. And like I said just now, if you have a closed circle on one and then you have this other section and they're not joined together at the same point, like this one's not joined together, then usually one is going to be closed and one is going to be open. So just keep that in mind. With this piecewise graph, we can determine domain and range and then evaluate some points with them. So domain for the graph, left, we can go towards negative infinity. And then right, even though there's a hole here, it's filled here. So technically that x is still accounted for. So we go left, and then we can still go right all the way through. So it's going to be positive infinity. So there is no break in the graph where we have to exclude a number. Range is bottom, so we're starting at 0, and it can include 0. And then 1, so it's a hole here, but it's filled here. So we can include 1, and it keeps going through to positive infinity. So there's my domain and range for this particular graph. When we evaluate, what this is saying is f of x is the function, and it's replacing -2 with the x. So it's asking you, it's giving you the input, which is x, and it's asking you for the output. So when x is -2, what is the output on your graph? So -2, the output is here at 3 for the y value. When x is -1, it hits the graph here at -1 for the x, and the output is y, which is 2. When x is 1, so it's here on the x, what is the output? So we actually have two outputs. We have this one and we have this one. But this one is technically no solution because it's open circle, so it doesn't include that point. So we don't want to use the y value of 1 because that gives me a non-valued number. Instead, we want to use the closed circle. So if we do the x value here, then our input is 1 and our output would be 0. So be careful when you have the two x values, two values that are x, two y values that are same x. Make sure you're using the right y. When x is 2, our y value here is 4. Okay, so that is how you do the piecewise functions. And then another thing I want to point out is what these little holes in the graph are actually called. So continuous functions are functions that have no break in them. So they just go on continuously and smooth. And then the discontinuity or discontinuous functions are going to be functions that have some kind of break in them of some sort. So you're going to have three types of discontinuities. The first one is called a removable discontinuity. And y'all are actually familiar with this one. If you went over rational functions in Algebra 2, then you probably learned about these things called holes in the graph. And those are actually removable discontinuities. So what they look like is when you would have a normally otherwise straight line or continuous graph, and then there's a disruption in that graph and then it just keeps going, that's a hole or a removable discontinuity. The second type is called a jump discontinuity. So this one is like what we just graphed. So you'll have a graph of 1, and then it might jump up and continue a graph of another. So when you have that jump discontinuity, most often you'll have an open circle and a closed circle right on top of each other. So it fills that spot on the range or domain in one spot and leaves it open in the other spot. So you jump up to get the other part of the graph, jump discontinuity. And the third is the infinite discontinuity. So infinite describes an asymptotic behavior. So if you had like a vertical asymptote and a horizontal asymptote, those asymptotes are boundary lines that the graph cannot go. So it makes the graph discontinuous there because it can't go through it. And they go on infinitely. So that's why it's called an infinite discontinuity. So anytime you see an asymptote in your graph, it's going to create an infinite discontinuity. Okay, so I'm going to skip over this example, but it will be on the key. So you can work this one on your own and then just check it with the key to see how you did. But we are going to talk about this one. So another way you can do piecewise functions is to see the graph already given to you and have to write the equation. So we're going to start with the left side of the graph, which is the left line. And it looks like it's going to be a piece of a parabola. So we're most likely dealing with a quadratic. So I'm going to show you one way if you don't know how to determine what your actual equation is, because it's not following the normal 0, 0, negative 1, 1, negative 2, 4. So it looks like it's been transformed in some way. So you could also, if you know your critical points of a quadratic, you can plot these out. So we've got 0, 0, and then this should be at negative 1, positive 1, and negative 2, positive 4. So it's been transformed to now include my 0, 0 still. So I know it hasn't shifted left, right, up, or down, because that would have changed my 0, 0. And then my other point that's right after 0, 0 is negative 2, 3. And then I can't see the other point. So we're looking at how did it change from negative 1, 1 to negative 2, 3. And we know it didn't shift left or right. So we can't just say, oh, it minus or subtracted 1, or it went down 1 or left 1. We can't say that, because it would have changed the 0, 0. So it's got to be some kind of stretch or compression where you're multiplying. So to go from negative 1 to negative 2 multiplying, you would multiply that by 2. So our x values got multiplied by a 2, and our y values went from 1 to 3, so they got multiplied by a 3. So if I put this in the transformation form, remember x values are controlled by the b and the c of your transformations. If you had a, b, x minus c plus d. Those are your 4 transformations that could occur. So a and b are the ones we're dealing with where they're multiplying. B and C are inside parentheses, and they are controlling the x point, and A and D control the y point. Also, if you recall, B and C are in parentheses, so you have to do the exact opposite of what you think you would do. So if I know that the A value controls the y, then this 3 is my y. So we would write it 3 parentheses, and then we have the one that's controlling the x, so that would be the b value. But we have to do the opposite of what we think we would. So instead of 2, it's going to be 1/2. And then x, there is no shift left or right, so we can just write it like that. So 1/2 x squared, we would have to square both the 1/2 and the x. So squaring 1/2 is 1/2 times 1/2, which is really 1/4. And x times x is x squared. And that is being multiplied times 3. So my final equation, 3 times 1/4, is 3/4 x squared. Okay, so some of yours are going to be a little bit more straightforward, to where you're not having to deal with a and b and find all your transformations, but you could see transformations in there. So I wanted to make sure you knew how to do the a and the b value again, since you did do it in Algebra 2, but it might have been a while. The domain for this one is going to be restricted, though. So here we can only do the x values this way. So that would be all the x's less than or equal to 0. So there's our first one, 3/4 x squared, comma, all the x's less than or equal to 0. And then we do the right line. So we start here at a y-intercept of -4, and this is linear. So I'm thinking in the terms of y equals mx plus b. So if we know y equals, the b value is your y-intercept, so that's going to be -4. And then it looks like my slope is going up 2 over 1 each time. So that's going to be 2 over 1, or just 2x minus 4. So second equation, 2x minus 4. With a restriction of everything greater than, because we're going to the right, everything greater than but not equal to 0 on the x. So x is greater than but not equal to 0. And we put our restriction in our final equation, and this is your answer for writing piecewise functions given the graph. So your homework for tonight is the assignment on WebAssign 1.2, and it's going over parent functions, piecewise functions, and greatest integer functions. So if you have any questions, email your teacher. Thanks, guys.